Good morning, students. Today we shall start with an interesting topic in the chapter nuclear. That is, we are studying two types of nuclear reactions. One is fission, another is fusion. So what is the importance of these reactions? The importance of these reactions is they release a tremendous amount of energy. Let us compare the energy released by the nuclear reactions with the energy released by the chemical reactions like burning of coal or petroleum. So the chemical reactions release energy in electron volt, whereas the nuclear reactions release energy in MeV, mega electron volt. Means how many times the energy is greater? Million times more. So energy released by the nuclear reactions is million times more than the energy released by the chemical reactions. That is why these nuclear reactions are very important. So today we shall define fission and fusion, and we shall find out the differences between fission and fusion. So let us come to the first one, that is nuclear fission. So in this nuclear fission, a heavy nucleus breaks into two light nuclei of comparable masses and there is a release of a large amount of energy. One single nucleus breaks into two parts. This reaction we call it as a fission reaction. Let us take the example of a uranium nucleus. It is represented as 92 uranium-235. Now, let us bombard it with a thermal neutron, 0 and 1. Thermal means the energy of the neutron is less, it is less than 1 electron volt. So, if you bombard this uranium with a neutron, then this uranium will capture the neutron and it will become unstable. So, after capturing the neutron, it becomes 92 uranium-236. Because it is unstable, I have shown it in a squared bracket. Now this unstable nucleus breaks into two parts. One is barium, another is krypton. And in this process, 3 neutrons are released together with 200 MeV of energy. So when you are writing this chemical reaction, you should take care that the atomic number and the mass number remain the same on both the side, left hand side and the right hand side. Suppose the mass number, if you compare it, is 235 plus 1, that is it is 236, and then if you add the mass numbers of the products, you should also get 236, that is 144 plus 89 plus 3, because 3 into 1. So the sum should be again 236. Similarly, the atomic number on the left hand side should be equal to the sum of the atomic numbers on the right hand side. Now let us go to the next one, that is we shall define what is nuclear fusion. So it is just the reverse, from two light nuclei go to a single nucleus. So what is nuclear fusion? Two light nuclei, they combine to form a single nucleus and in this process energy is released. Let us take the example of the fusion of two deuterium nuclei. Deuterium is represented as 1s2. So, two deuterium nuclei are combining, 1s2 plus 1s2. So, after combining, it becomes a helium nucleus, 2He4, and in this process, 24 MeV of energy is released. So, this is the definition of nuclear fusion. That is, two light nuclei combine to form a single nucleus together with a release of energy. Now, in both the processes, fission and fusion, energy is released. So, let us find out why energy is released in fission and fusion. The explanation is saying that what we had defined for the formation of a nucleus in the previous lecture. So, using Einstein's mass energy relation, we had shown that during the formation of a nucleus, energy is released. The same reason is applicable here. So, in this nuclear reaction, suppose you take fusion reaction, these are the reactants and this is the product. You expect that total mass of the reactants should be equals to the total mass of the products. But it is found that the mass of the reactants is always greater than the mass of the products. The meaning is, in fission and fusion, there is a certain loss in mass. So this loss in mass will be equivalent to a certain amount of energy, because according to Einstein's mass energy relation, E equals to mc square, mass and energy are equivalent. So this loss in mass is equivalent to energy. Therefore, energy is released in these nuclear reactions. Let us find out how much energy is released in these reactions. Let us say loss in mass is delta M. So how much energy will be released? Replace M by delta M. So energy released will be nothing but E is equals to delta M into C square. So here delta M is in kilogram, then the energy will be in joules. But usually in nuclear physics we use a smaller unit of mass, that is atomic mass unit U. So delta M will be usually in U. So you have derived the relation 1U is equals to 931.5 MeV of energy. So if the loss in mass delta M is in U, then the energy released will be nothing but delta M into 931.5 MeV of energy. So this is how you calculate the energy released in the nuclear reactions. So you can expect a 5 marks problem based on calculation of energy released. Now let us try to compare fission and fusion. So the first point of difference is the definition itself. So what is the definition of fission? That is two heavy nucleus breaks into two light nuclei together with a large amount of energy. And what is the definition of fusion? Two light nuclei combine to form a single nucleus together with the release of energy. Now next we shall compare the energy released in both the reactions. In one fission reaction, how much energy is released, and in one fusion reaction, how much energy is released, and which energy is larger. So in one fission reaction you have found here 200 MeV of energy is released, and in one fusion reaction only 24 MeV of energy is released. So which energy is more? This energy released in fission reaction is more. So what will you write regarding the second point? Energy released per reaction is more in fission reaction and it is less in the fusion reaction. But let us find out energy released per nucleon of the reactants. What is the meaning? So here how many nucleons are involved? So it is 235 plus 1. That is total number of nucleons is 236. And this energy released is 200. So energy released per nucleon means you will find out 200 upon 236. So it comes out to be 0.85. So in fission reaction 0.85 MeV of energy is released per nucleon. Let us find out how much energy is released in the fusion reaction. Here how many nucleons are involved? 2 plus 2, 4 nucleons are involved and the energy released is 24. So how much is the energy released per nucleon? It will be nothing but 24 upon 4. So it will come out to be 6 MeV. So which energy is larger? Energy released in fusion is larger when you take it as per nucleon. So that is my third point. So energy released per nucleon of the reactants is more in fusion and less in the fission reaction. Now coming to the control of energy. In both the processes energy is released. Which energy can be controlled and which cannot be controlled. So it is possible to control the energy released in the fission reaction. So a nuclear reactor is based on this. We shall come to that later on. So you can control the energy released in the fission reaction, whereas you cannot control the energy released in the fusion reaction. So that is what I have written as the next point. Energy released can be controlled in the fission reaction and it is not controlled in the fusion reaction. Then just now I told you this is a thermal neutron, means it has got lesser energy. So this fission reaction is possible at ordinary temperature, that is it is possible at room temperature, whereas for fusion reaction you require a very high temperature. What is the order of the temperature? 10 raised to 9 Kelvin. So why such a high temperature is required for nuclear fusion? So here we are combining two nuclei. So you know nucleus is positively charged. So both the nuclei are positively charged. So if the two nuclei have to combine, they should overcome the repulsive force between them, because between two positive charges there will be a force of repulsion. So if the two nuclei have to combine, they have to overcome the force of repulsion between them. And to overcome the force of repulsion, these nuclei should have a very high kinetic energy, and this is possible at a very high temperature. So at a high temperature, the kinetic energy of the nuclei will be more, so they can combine to form a single nucleus. That is why a high temperature is required for nuclear fusion, and this temperature is about 10 raised to 9 K. So this is another difference between fission and fusion. Fission is possible at room temperature or ordinary temperature, but for fusion you require a very high temperature, about 10 raised to 9 Kelvin. And another difference is the products in the fission reaction are radioactive, whereas they are non-radioactive in the case of fusion reaction. So these are harmful, these are harmless. So these are some of the differences between fission and fusion. So let us summarize what we have done now. First is, we have defined two types of nuclear reactions. One is fission, another is fusion. And we have seen that in both the reactions a large amount of energy is released, because in both the reactions, when the reaction takes place, it is found that mass of the reactants is greater than mass of the products. So there is certain loss in mass, and because of the loss in mass, energy is released in both the reactions. So you can calculate the energy released in the reactions using the formula E is equals to delta M into 931.5 MeV of energy, where delta M is the loss in mass expressed in U. Then we have found out the differences between fission and fusion. What are the differences? First difference is the definition itself. Here a heavy nucleus splits into two light nuclei with release of energy. Here two light nuclei combine to form a single nucleus with release of energy. Then we have compared the energy release in both the reactions. We have found that energy released per reaction is more in fission and it is less in fusion reaction. Then the energy released per nucleon of reactants is more in fusion and it is less in the fission reaction. And we can control the energy released in the fission reaction, and the energy released in the fusion reaction cannot be controlled. Then the fission reaction takes place at ordinary temperature or room temperature, whereas the fusion reaction requires a very high temperature, about 10 raised to 9 K. Then in the fission reactions, the products are radioactive, whereas in the fusion reactions, the products are non-radioactive. So these are some of the differences between the fission and fusion reactions. And the common point is both the reactions release energy. We shall define the term chain reaction. So actually this is a chain of a number of fission reactions. Just now we have studied the fission reaction. Let us write that fission reaction. A uranium nucleus is bombarded by a thermal neutron. It breaks into two fragments, barium and krypton. In this process, 3 neutrons are released together with a large amount of energy, 200 MeV of energy. So let us show this reaction diagrammatically. And let us consider that we have a sample of uranium. That is, we don't have a single uranium nucleus. We have a sample of uranium. There are a number of uranium atoms inside the sample. So what we do is, we start the fission reaction by a single neutron. So a single neutron strikes a uranium atom. So it undergoes fission. Then in this process, 3 neutrons are released. What these 3 neutrons will do? There are a number of uranium atoms. These neutrons will cause the fission of other uranium atoms, producing more neutrons, and this process goes on continuing. How long? Until all the uranium atoms undergo fission, that is, they are disintegrated. So this is a chain of a number of fission reactions. So it is called as a chain reaction. And it continues by itself. Once you start the fission reaction, on its own further fission occurs. So it is called as a self-propagating reaction. So how to define a chain reaction? I have written the definition here. It is a self-propagating reaction in which the fission continues by itself. On its own the fission occurs. So such a reaction is called as a chain reaction. Now we have a number of generations of neutron. So from the figure, let us name them as, say this is first generation of neutron, this is the second generation of neutron, this is the third generation of neutron, and so on. So we have different generations of neutron. Now we shall define a term called as neutron multiplication factor. It is denoted by the letter K. What is the definition of K? K is defined as the ratio of number of neutrons in any one generation to the number of neutrons in the previous generation. Now let us take different values of K. So accordingly we will have different types of chain reactions. Now let us first take K value greater than 1. K is greater than 1. The meaning is numerator is greater than the denominator. So number of neutrons in any one generation will be greater than that in the previous one. So here that is what is shown here. Suppose you take any one generation, second generation, there are 3 neutrons. It is greater than the previous one, that is 1. Suppose you take number of neutrons in the third generation, there are 9 neutrons. So this is greater than that in the second generation. So here the number of neutrons goes on increasing rapidly. So second point I have written here, number of neutrons increases rapidly. So if the number of neutrons increases, the fission also increases. So here only one fission occurs. So how much energy is released? 200 MeV of energy is released. So here 3 fissions are occurring. So how much energy is released? 3 into 200 MeV of energy will be released. Now here 9 fissions are going to occur. So how much energy will be released? 9 into 200. So what about the energy released? It is uncontrolled. So there is no control over the energy. It increases very rapidly. So energy becomes uncontrolled. And because the energy is uncontrolled, such a chain reaction is called as uncontrolled chain reaction. It is also called as supercritical chain reaction. So here the number of neutrons multiply indefinitely until the whole uranium sample undergoes fission. So it results in a violent explosion. So this is actually the destructive use of nuclear energy. Atom bomb was dropped on the 2 cities in Japan, Nagasaki and Hiroshima. So this destructive use of uncontrolled chain reaction is nothing but an atom bomb. So the use is an atom bomb. And you can imagine how much energy is released. Suppose you compare energy released by uranium atom to that of coal. It is found that 1 kg of uranium is equivalent to 16,000 kilogram of coal. So this is how the nuclear energy is very tremendous. So this is the first type of chain reaction. What we have studied in this chain reaction, multiplication factor is greater than 1. Number of neutron increases rapidly. There is no control over the energy. It gives uncontrolled energy. So it is called as uncontrolled chain reaction. And the use is in an atom bomb. Now let us take the next value of K. Let us say K is equals to 1. So K value is 1. The meaning is number of neutrons in any one generation should be equal to number of neutrons in the previous generation. So how this is possible? So this is possible like this. So in the first generation you have 1 neutron here. Now this is producing 3 neutrons. So let us cut these 2 neutrons. Let us not have these 2 neutrons. So we shall make use of only 1 neutron. These are allowed to escape from the system. Yeah. So they are cut down. So 1 neutron is producing only 1 neutron. So in the first generation there is 1 neutron. In the second generation also we have kept it as 1 neutron. Now this 1 neutron again will cause 3 fission. Again these 2 are cut down. Only this is allowed. So again you have 1 neutron in the third generation. So in each generation the number of neutrons remains the same. So here the number of neutrons remains constant. So if the number of neutrons remains constant, what about the energy? Here one neutron means one fission, here again one neutron means one fission, and so on. So in each fission only 200 MeV of energy will be released. So every time only 200 MeV of energy will be released. So energy released is now controlled, and because the energy release is controlled, such a reaction is called as control chain reaction. Actually, this is the constructive use of nuclear energy, where you are controlling the energy, and this is done in a nuclear reactor. So we are studying in detail nuclear reactor in the next point. So this is about your control chain reaction. So what are the points in the control chain reaction? The K factor is equals to 1. Therefore, number of neutrons remains constant, and the energy is controlled, and such a reaction is called as a control chain reaction. It is also called as critical chain reaction, and it is used in a nuclear reactor. So this is a destructive use of nuclear energy, atom bomb, and this is a constructive use of nuclear energy. Now the third type is K is less than 1. What is the meaning of K is less than 1? If K is less than 1, numerator is less than denominator, the meaning is number of neutrons in any one generation is less than that in the previous generation. So how this will happen? You can look at this figure in the reverse way. Starting, suppose there are 9 neutrons, then they become 3 neutrons, then they become 1 neutron, like this. So the number of neutrons goes on decreasing. So if the number of neutrons decreases, what about the energy? The energy also will decrease, because fission is going to decrease, and finally the nuclear reaction will stop after certain time. So this is called as a subcritical chain reaction. So this is the third type of chain reaction. So let us revise the points we have done now. First point we have defined is what is a chain reaction. Chain reaction means it is a chain of a number of fission reaction. What is the actual definition? It continues by itself. So it is called as what reaction? It is a self-propagating reaction in which the fission continues by itself. Now we have defined the neutron multiplication factor as number of neutrons in any one generation to the number of neutrons in the previous generation. Let us take 3 values of K. First value of K is greater than 1. If K is greater than 1, what happens? Number of neutrons increases rapidly. Therefore, the energy also increases rapidly. There is no control over the energy. So, it gives uncontrolled energy. So, such a reaction is called as uncontrolled chain reaction. Second value is K is equals to 1. Then the number of neutrons remains constant, and it gives a controlled supply of energy. So, it is called as a controlled chain reaction. Third type is K is less than 1. Therefore, the number of neutron decreases, the energy also decreases, and it stops after a certain time. Then what are the uses of these reactions? Uncontrolled chain reaction is used in an atom bomb, and controlled chain reaction is used in a nuclear reactor. So this is all for today's session.